DFG Science TV, Discrete Optimizers. Many roads lead to the destination. How math simplifies our daily life.
When we bake a pizza, we follow a recipe step by step. When children build a model out of Lego bricks, they sometimes follow the instructions. Even when mathematicians develop a way of solving a problem, they describe it with instructions of a kind. These instructions are called an algorithm. But what are they like? Let's take the general problem of finding the shortest route from a starting point to a destination in a network once again. The simplest algorithm calculates every path imaginable from A to B and then tells us which is shortest. You'd expect a computer to manage that pretty fast, but you'd be wrong. There are simply such an incredible number of possible ways. Even if a computer could try out 1 billion ways per second, it would still take months to find the shortest route from Munich to Berlin, for example. And sometimes we do like results a bit faster than that.
Die Route wird berechnet.
Discrete mathematics and computer science have many things in common. For example, the computer scientist Edsger Dijkstra realized that it's possible to exploit a special characteristic of this problem. On any shortest route, every part of the route also has to be a shortest path. If that wasn't the case, any shortcut on any part of the route would also be a shortcut of the overall route between the starting point and the destination, which is impossible. Dijkstra's algorithm finds the shortest path from one node to the next, starting from the starting node and continuing until it eventually reaches the destination node. In this way, the algorithm is able to rule out a lot of pointless options at once. For example, if we start with the starting node and begin by looking at its nearest neighbours, no matter which route we subsequently take, we now know that we have to take one of the paths with the yellow edges. A shortest edge is thus simultaneously the shortest path to the next node. We'll mark it in red, as we found the shortest route for this step already. Now we'll look at all of the nodes around this node. Just like in the first step, we find another node, for which we know that the current route via the yellow edges is also a shortest route. We gradually apply this process step by step to the entire graph. We may find that there are routes that we found in the first steps that we can improve on. In this way, we even know that some edges can never be on any shortest route from the starting node. In the end, we're left with just one shortest route. Now we've seen our first algorithm. The mathematicians are just working on an algorithm for their current project on the Kiel Canal.
Well, we could apply a shortest path algorithm to the Kiel Canal too, couldn't we?
Of course we could. After all, we're looking for the shortest path for each ship passing through the canal.
And we could then simply use the waiting times and the turnouts to wait the edges.
But I think that the algorithm itself also needs to be expanded a bit.
That's right, because whenever a large ship is in the canal, in other words travelling along an edge, this edge is closed to other large ships. If they also want to use the canal, they have to wait in the turnouts. We still need to teach the algorithm that.
If we have to think out new algorithms, then we have to be creative.
The mathematicians have written their algorithm in programming language that the computer can understand, and now they can begin with calculating the first routes along the Kiel Canal. Their solutions are presented in the way the planners are accustomed to. In the next episode, we'll see how networks can become so large that they're too big for the computer to handle. Then the discrete optimizers have to come up with a new idea.
Visit DFG Science TV for more information. Awaken the researcher within you.